Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture on the use of MATLAB for doing forward kinematics and inverse kinematics of a manipulator system. In the last two lectures, I talked about forward kinematics and inverse kinematics, what it means and how do we, the various steps that are involved in doing forward kinematics and inverse kinematics. Today we'll write a program in MATLAB that can automatically do forward kinematics and inverse kinematics and can also do a simulation. For example, if you give it the joint angles, it will take the end effector to the desired position and orientation. Or if you give the position orientation and do inverse kinematics, it will give you the joint angles. And also do a simulation, which is actually going to show how the manipulator is moving. Okay, so today we'll look at how to write a MATLAB code which can compute and also do simulation of a manipulator as it is moving. So today's lecture is on writing a MATLAB code for forward and inverse kinematics of manipulator system. Now, I discussed about the various steps involved in doing forward kinematics and inverse kinematics, and today I'll talk about how to write a MATLAB code that can first of all compute. Okay, so it should be able to compute the end effector position and orientation. Okay, that is in forward kinematics, and in inverse kinematics it should be able to find the joint angles. Okay, so these are two things which the code should be able to do. And after doing the forward kinematics or the inverse kinematics, it should be able to simulate the motion also. Okay, so this is something which we are going to see how to write a very simple MATLAB code which can do that. Now in forward kinematics, it should, given the joint angles, suppose I give it theta 1 and theta 2, it should be able to find the position and orientation. And suppose I give it some end effector coordinate xy, it should be able to find the joint angles. Okay, and also simulate it. Now, very briefly, talking about what I mean here is we have a two-link manipulator. Okay, this is two links, and the manipulator is like this. Okay, this is my joint angle theta 1, this is my joint angle theta 2, and this is my joint angle theta 3. This is link length L1, link length L2. Now, suppose I give theta 1 and theta 2 as input. The manipulator should be able to compute what is the end effector, what is the position here, okay, xy, and then simulate and take it to that point. Now, if you look at the right side bottom here, the simulation. So in this case, we have a two-link manipulator having 2 degrees of freedom. Okay, and it has 2 revolute joints, and you can see it at angle theta 1 equal to 0 and theta 2 equal to 0. So theta 1 is equal to theta 2 is equal to 0 degrees here in this configuration. Now, suppose I give input, the desired input is theta 1 is equal to 40 degrees and theta 2 is equal to 60 degrees. Okay, it should be able to compute what is the xy and also take it there in a simulation and actually show how it is moving. That is the objective of today's class. So I'll just show you how it runs. So when I run this simulation, you can see that it is moving, two links are moving, and it will go and stop at theta 1 equal to 40 and theta 2 equal to 60. So let's see the simulation again. So this is my 0, 0, the base of the manipulator. And I have given my desired input as theta 1 equal to 40 degrees and theta 2 equal to 60 degrees. So what the MATLAB program is doing, it is computing the various positions of joint 1 and joint 2, and it is moving it like that. And it's also plotting and showing you that this is how the manipulator is moving. So let's see it again. And finally, it will go and stop at theta 1 equal to 40 and theta 2 equal to 60. This is what we mean by a simulation. Okay. So today's class is basically how to write a MATLAB program, okay, which can do this and which can also simulate like this. Now, what are the steps involved? The first thing is, given a manipulator system like this, 2R manipulator, which is very simple, the first thing that we need to do is to make our DH parameter table. Okay. Now, in this simulation, what is it that we want? What we want is the positions of these 2 points. One is the base point, which is not moving, so we don't care about that because it is 0, 0 always. This is the point of joint 1, this is joint 1 which is moving, and that is joint 2 which is moving. So if I can find this point and this point as it is moving in space, then I can plot it very easily, and that is what a simulation is. So what is the objective? The objective is to find this point, joint 1 and joint 2, as it is moving, and connecting these two joints by straight lines, we get this link structure. Okay, now how do we get this point and this point? So the first thing that we do is to make our DH table. Well, before that we have to put our axis. So this is my Z0 and Z1. This is my Z2. Okay, let me write it. Let me erase this. This is my Z2. That's my Z3. Okay, this is my this side is X0. This is X1. This is my X2, and that's my X3. The link lengths are L1 and L2. So what is the DH parameter table here? The DH parameter table, which I have done it in 1 or 2 classes earlier, A alpha D theta. Okay, please refer to the details of that. I'm writing it very, very quickly here. So this is L1 0 0 theta 2, L2 0 0 theta 3. This is 1 2 3. Okay. So from the DH parameter table for this manipulator, what do? We get the various transformation matrices T0 to 1. Okay, T0 to 1 is given by cos 1 minus sin 1, sin 1 cos 1 0 0 1. Okay, this is 0 0, this is 0 0 0, and that is 0 0 0 1. It's my first matrix. Okay, what is my second matrix? T1 to 2 is cos 2 minus sin 2, sin 2 cos 2 0 0 1 0 0 0 0 0. This is L1 0 0 0 1. And what is T2 to 3? This is the third one, which is equal to 1 0 0 0 1 0 0 0 1. This is an identity matrix. This is L2 0 0 0 0 0 1. Okay, so if I just go back to the manipulator structure, so we see that I'm interested only in this point XY. That is why the last the third one I have made it into identity matrix. Okay, so I'm interested in this point and I'm interested in this point, not beyond that. Now, what are we trying to do? We are trying to find the points. Which 2 points? So one is this point, which is always 0 0. The second point is this one, which is joint number 1, which is, let's say, x dash y dash, and then which is joint number this is this is joint number 1, joint number 2, and this is joint number 3. Okay, this is joint 1. Now, how do I get this point and how do I get this point? I know the transformation matrix from one link to another link. So this joint here will be equal to the transformation matrix T0 to 2, which is equal to T1 0 to 1 cross T1 to 2. Okay, so this will give me the matrix. Okay, cos 1 2 minus sin 1 2 sin 1 2 cos 1 2. Sorry. Yeah. So okay, and it is 0 0 1. This is something we have seen in the couple of classes behind. This is 0 0 1 0 0. Here it is the first which is going to give me L1 L1 cos 1, L2 sin 1. This is 0, that is 1. Okay, so this is what it is going to give me. Now this let me change the color. So the last column here is the one that is going to give me the position of this point with respect to the base frame. So this is my base frame 0 0, right? This is my x, that's my y. So this is the matrix, the last column. This is going to give my x coordinate, and that is going to give my y coordinate of this point. Okay, so when it is moving, what we can do is I have to track this point, and as theta is changing, so L1 cos theta 1, L2 cos sin theta 1 is, as theta 1 is changing, this point will change, right? So by using this matrix T0 to 2, I can actually get from the fourth column, I can get what this point x dash y dash is. Now for joint number 3, this point xy, how do I get that? Now I take the full matrix T0 to 3, and if you multiply it out, what do we get? Cos 1 2 3 minus sin 1 2 3 sin 1 2 3 cos 1 2 3. This is 0 0 1 0 0. Okay, and this is 0 0 0. What is here? L1 cos 1 plus L2 cos 1 2, L1 sin 1 plus L2 sin 1 2. This is 0, this is 1. I have derived all these things in 1 or 2 classes earlier. Please refer to those notes for details. Again, here what we see is that the last column here, okay, this is the one that gives me the x coordinate. This is my x coordinate, and this is my y coordinate. This one, it gives me my y coordinate. Okay, so by using this transformation matrix and looking at the last column of it, we can actually find what is the coordinate of this point and what is the coordinate of this point. Okay, so this is the use of the transformation matrix, which can also be used for simulation now. So now let me come back to how do we write the program. Now how we write the program is for joint number 1. So for let me draw and explain again. Okay, so this is my manipulator. Okay, it is initially here, it is at 0 0 position. Now so theta 1 is equal to theta 2 is equal to 0 initially, okay, at stage 1. Then I give an input of theta 2 is equal to 40 degrees and theta 1 equal to 40. It can be anything. Theta 2 is equal to 60. Okay, this is at point 2. Now what we do is theta 1 is moving from 0 degrees to 40 degrees. Okay, and then theta 2 is moving from 0 degrees to 60 degrees. Okay, this is the motion. Okay, so now what we are saying is how we'll do the simulation is, I know this is going to move, the final position is here. So where is theta 1? Theta 1 is 40 degrees. Let's say 40 degrees is here. Okay, and where is theta 2? Theta 2 is 60 degrees. It is here. Okay, so this is my theta 1, theta 2. Okay, so what I will do is, I know the motion is for theta 1 is 0 to 40 degrees. I will divide this 0 to 40 in 100 units, interval of 100. I'm going to divide this into 100 divisions, equal divisions. Okay, similarly, theta 2 is going to go from 0 to 60 degrees. I'll divide this into 100 divisions, equal number of divisions for theta 1 and theta 2, otherwise it won't match. Okay, then for each of these divisions, what I will do is I will go back to this equation. I will go back to this matrix. This will give me the joint 1 position, and this will give me the joint 2 position. So I will use this transformation matrix. Look at that last column, L1 cos 1 and L2 sin 1. This is going to give me x dash and y dash, so the position of this joint. And similarly, T0 to 3, the last column is going to give me the x and y of this joint. Okay, so what I will do is, as I'm incrementing this, I will start with theta 1 equal to 0, theta 2 equal to 0, and slowly keep increasing. Okay, so this will probably be 0.4, 0.6, okay, in the first one. Okay, so what I will keep doing is, at every step, I'm going to have a for loop, which is going to run from 0 to 100. Okay, and so what it will do is, for every I equal to 0, then the next step, it will keep doing that and keep incrementing theta 1 and then incrementing theta 2, and then going back to this equation, going back to this matrix and computing what is x dash and y dash, and then it is going to plot x dash and y dash and connect it by a straight line. That is the meaning of a simulation. Okay, so I hope it is clear how we are trying to solve this problem. We are finding the DS parameter table. Then from the DS parameter table, we are finding the transformation matrices, and from the transformation matrices, we are coming to the last column of it, looking at the position of x and y, and then we are simply going to plot x and y connected by a straight line. And as it is incrementing, first, second, third, fourth step like that, it will appear that this is moving. Okay, that is how the simulation that I showed. So this is the meaning of a simulation. Okay, it will appear that it is moving like this. Okay, in how many steps? In 100 steps, because I have made this into 100 divisions. You can have any number of steps. That is the basic formulation, how this simulation works. Okay, so very quickly I'll look at the program, and then we will proceed by seeing how the program is written, and then how you can see the program. Okay, so let's look at how the program is written. So let's go back to the program here. So we are going to MATLAB. In MATLAB, this is the program. Okay, so this is the program that is there. So this is forward kinematics of two-link planar manipulator. The planar manipulator is two-link arm to our planar, the one that I just showed. Now you have to define the link lengths L1 and L2. So we are defining the two link lengths here in L1, and L1 is equal to 10 and L2 is equal to 10. Okay, then we have to specify the initial configuration. So I said the initial configuration is 0 and 0 degrees. Okay. Now we are saying that there are two thetas, which is theta 1 and theta 2. So the initial theta 1 is equal to, I'm saying 40, and sorry, not initial is 0 and 0. So I want it to go to theta 1 equal to 40 and theta 2 is equal to 60. In forward kinematics, the input is the joint angles, and it will take you to the corresponding position, right? So I'm giving the input as, or my desired joint angles are 40 and 60. Okay. Now, as I explained, the joint 1 will go from 0 degrees to 40 degrees, and joint 2 will go from 0 degrees to 60 degrees. Okay. So I am going to divide this into 100 division. So this line space basically means that we are dividing the theta initial 0 to theta final, which is 40, into 100 units. Similarly, theta 2 is we are dividing, the line space is dividing theta 2 initial to theta and 2 theta 2 final by 100 into 100 units. Okay, 100 divisions rather. Okay, then what we do is we make our DH parameter table. Now this for I is equal to 1 to 100 essentially explains that I is an index which is going from 1 to 100, and these are the 100 divisions I have made. So every step it will start from 0, then it will take the next one. It will be 0.4, 0.6. It will keep incrementing the angles and then computing what is the corresponding position of the joint 1 and joint 2. So the procedure for writing it is, first we make the DH parameter table. Okay, so A alpha D theta in program I'm writing it like this. Okay, so it was 0 0 0 0 theta 1, right? So this is a matrix, just the one that I wrote some time back. Okay, so A is the link length, it is 0 L1 L2, alpha is 0 0 0, D is 0 0 0, and theta is theta 1 theta 2 and theta 3. Here I'm simply writing as 0. Okay, now this was written the other way, but it is exactly the same. So it will be the DH parameter transpose is this one now. Now calculating the transformation matrices. So these are the three transformation matrices. The first one is T1. So it is cos minus sine, sine cos, and 0 0 0. Okay. The second one is cos 2 minus sine 2 A2. Okay, and the third one is 1 0 0 A3. Okay. So these are the transformation matrices that we are writing. Okay. Now, what is the position of joint number 1? So what are we interested in? We are interested in getting the position of joint 1 and joint 2. So you can see that joint position 1 is transformation matrix 1 into transformation matrix 2. Okay, and this is getting multiplied by this vector 0 0 1. Why? Because we want only that 4 1 coordinate of the, this is a 4 by 4 matrix. So the first element of the fourth column. Okay, so basically the 1 4 element we want. So in order to get that, we are multiplying this with 0 0 1. Now you can also get that simply by writing joint position on this matrix taking the element 1 4. That also is possible. Now joint position 2 is basically transformation matrix 1 into 2 into 3, and this is equal to getting multiplied by 0 0 1. Again, when we are multiplying these three matrices, I want the 4 1 element. Okay, so what it is doing is it is giving me the, so x and y are, it is starting from 0 0 is the base, then it is joint position 1 and joint position 2, then joint 2 position 1 position 2. Okay, so this is what we are doing to get the column of that matrix. Now there are different ways of writing a program. You know that you can write a program in different ways. This is just one way of writing a program. The other way of writing a program would be that the way I had written my T1, T2 and T3 matrices, you can simply write this as cos minus sine 0 and here also 0. Okay, and then second one will become A1, A2 and then A3 here. Okay, that's also possible. So there are other ways of writing it. The way I wrote it was a little different. Now here what this program has done is it has taken cos 1 minus sine 1, A1 here, sine 1 cos 1 0 0 0 0 1 0 0 0 1. Okay, so basically what I'm saying is the last column, the last element, that is 1 4, the way I wrote it was cos minus sine. Okay, because it is corresponding to that first A1 of, to the first link length, which is 0. Okay, so it's just a little different way in which we have written it. Okay, now so what are we getting? We are getting our joint position 1 and joint position 2. Okay, and then what we are doing is we are coming down and we are plotting. So we can plot the x and y. Now what is x and y? X and y is an array. X gives me the position of joint 0, which is 0. Then joint position 1 is the x of joint position 1. Joint position 2, position 1 is the x coordinate of joint position 2. Okay, this is written in an array. And we are plotting basically x and y. Okay, x and y, this is an array. So first of the base, then of the joint 1, then of joint 2. Okay, and then we are simply connecting these lines by a line, okay, and with a particular color, and we have used a grid just to show how it is moving. Okay, so this is essentially how the program is written, and there are of course different ways of writing the program. Okay, this is just one way. You can write it in any other way you want, but the basic structure remains the same. Now here something to note is what was the input. The input was theta 1 equal to 40 and theta 2 equal to 60. Okay, so let's run the program. So when we run the program, what you see is it is going to plot. It will start from 0, from the position theta 1 equal to 0, theta 2 equal to 0, and then take it to the position theta 1 equal to 40 and theta 2 equal to 60. Okay, so let's run it and see what it does. So we have run it now, and you can see that it is plotting as a simulation. So it starts from 0, then it goes to the next. It is moving like this, and then finally coming to the end, where is theta 1 equal to 40 and theta 2 is equal to 60. Okay, now this is what we mean by a simulation. So the word simulation sounds very nice, but this is essentially what we are doing. We are tracking the positions, those black dots, with the 0, 0, joint 1, joint 2. Okay, and then what we are doing is we are simply connecting them by blue color lines. So if you look at the plot command here, so plot xy is basically plotting the x and y coordinates of joint 1, joint 2, joint 3, and then connecting by blue lines with a line width having some line width. Okay, so this is essentially what we have done, and then x label, y label, title is put forward kinematics of two-link system, and the units which are marked on the x coordinate, y coordinate. Okay, so the grid is put to basically show you, or to just to give a better understanding of how this program works. Now let's run it again. So what I'll do again is I'll run this again. So I run it from here, and it starts from there, and then goes and meets 40 and 60. Okay, now suppose I change this now. So this is my forward kinematics. So what is the input? Input is the joint angles, right? Theta 1 and theta 2. So now here, suppose I put different joint angles. Let me change the joint angles to, let me make this 90, and let me make the other one 90 also. Theta 2 is also 90. Okay, now let me run it and see what it does. So when I run it now, it is starting from 0, 0, again doing the same thing, but now the final position will be different. Okay, so that's my theta 1 equal to 90 and theta 2 is equal to 90 also. Okay, this is forward kinematics. Now I can change it again just for fun. Okay, so you can change it again for just for fun. You can make this say 120. Okay, and we make the other one also 120. And let's run it again and see what it does. So starting from there, the angles were 0, 0. Then the desired angle, final angles are 120, 120. So you can see that it is coming to 120 and 120. Okay, so this is actually showing you how a forward kinematics program can be written in MATLAB. It's very, very simple. You can simply write it in MATLAB and you can simulate it. And it's the word simulation sounds very nice and fascinating, but this is what a simulation means. What are you essentially doing? Essentially, you're tracking those black points, okay, which are the joints, and then you're connecting by straight lines. And this is what we mean by a simulation. Okay, so next what we'll do is, so this is my forward kinematics. Next what we'll do is we'll look at inverse kinematics. Okay, so next I will want to look at inverse kinematics. So I'll just explain a little bit on inverse kinematics, and then I'll move on to inverse kinematics. So in inverse kinematics, what we do is we are given the position orientation of the end effector and I have to find the joint angles. Okay, So inverse kinematics is a little bit more involved as compared to forward kinematics, in the sense that in inverse kinematics you can get multiple solutions. So in inverse kinematics, there are basically two ways of doing inverse kinematics. The first way is the one I had explained, I think, in the last lecture, where we have a manipulator like this, and we have a link. Okay, these are my two links, the same manipulator, end effector position xy. Okay, now we can find cos 2 from the equation x is equal to L1 cos 1 plus L2 cos 1 2, and y is equal to L1 sin 1 plus L2 sin 1 2. Squaring and adding what we did get, we can find cos theta 2 is equal to x squared plus y squared minus L1 squared minus L2 squared divided by twice L1 L2. From here we can find sin theta 2. Okay, and once we find sin theta 2, we can get theta 2 as a tan 2 sin 2 cos 2. Okay, this is one way for getting theta 2. Now what about getting theta 1? How do we get theta 1? We make this construction, and this is my triangle, and what we do here is, this is my angle theta 1, this is my angle theta 2, which we have got. This is L1, this is L2. Right, so what we do is we define this angle alpha and this angle as beta, and then what we do is we find tan. So tan of tan alpha, so this is my angle alpha, this is my angle beta, right? So tan alpha is equal to y by x, and what is tan beta? Tan beta is equal to, this is L1, this is L2. Okay, so which is equal to L2 sin theta 2 divided by L1 plus L2 plus L2 cos 2. Okay, then we can find theta 1 as tan of theta 1 as tan of alpha minus beta, and then we can find what is theta 1. Okay, so this is a geometrical method of doing that. Now this is method 1, which I explained in the last class. Now there is other methods also where we can do inverse kinematics and try and find. So what is the other method? The other method is as given in the textbook Craig. Okay, you can please refer to this textbook Craig, Introduction to Robotics by Craig. Intro to Robotics by Craig. Okay, now here what the proposed method uses the law of cosines. So these are two links. Okay, and this is my angle between them. This is L1, this is L2, and this is my minus theta 2. Okay, this is my theta 1 angle. Okay, so now the method that is used here is using the law of cosines. This is my xy, so x squared plus y squared is equal to L1 squared plus L2 squared minus twice L1 L2 cos of 180 plus theta 2 is used. Okay, so we look at the upper triangle. Let me change the color. So we look at this triangle here, this triangle, this triangle, this triangle, and by the law of cosines we get this. And we also know that cos of 180 plus theta 2 is equal to minus of cos theta 2, right? So from here we can find that cos 2 is equal to x squared plus y squared minus L1 squared minus L2 squared divided by twice L1 L2. Okay, so we can get our cos 2 from here. Now how do we get, now something to note here is that we are actually finding the upper solution, so it is minus of theta 2 which we are getting. Okay, now how can we find the other solution? So to find the other solution, what we are doing is we are finding our angle exactly in the similar way. We are finding, I'm saying this angle, this is the other solution. Okay, this is the other solution, one solution on top, one solution at the bottom. So this solution is my beta, this angle rather, and this angle is pi. Okay. So what we are doing is we are finding these two angles phi and beta, just like in the previous case, and then finding the other solution. Okay, so what we are doing here is we know that this constraint is there, x squared plus y squared root over has to be less than L1 plus L2. Okay, so x squared plus y squared is the hypotenuse. So the hypotenuse has to be smaller than the other two sides. Otherwise, it means that that point xy is outside. Okay, this is to check that xy is inside work volume. Because if it is outside the work volume, then obviously it can't reach that point. So this check is required in inverse kinematics. Forward kinematics, it doesn't matter. So from here, what we can do is defining these two angles beta and psi. Beta is equal to a tan 2 yx, y and x, right? And cos psi is equal to x squared plus y squared plus L1 squared minus L2 squared divided by 2L1 root over x squared plus y squared. Okay, and theta is equal to, theta 1 is equal to beta plus minus phi. So this is the solution that is also a geometrical solution as given in the textbook reg. Okay, so the program has been written for this solution. Now how do we proceed with the program? Exactly like we did in the previous case. So we have a two-link manipulator. So this is my two-link manipulator. Okay, theta 1, theta 2. We first we assign our axis. Okay, from the axis we make our DH table, which I did, the same manipulator, so it will be the same DH table. Okay, then I make my transformation matrices, T matrices. Okay, T1, T01, T1 to 2, T2 to 3. Okay, and once we do this, what we can do is okay, we can find our joints. So when it is moving, okay, I want to find I'm given in inverse kinematics, I'm given the position and of the end effector. So I'm given this position, for example, I want it to go there. Okay, and I have to find this solution. This is one solution. Okay, so what I do first is I need to check, and there are two solutions, one that side, one this side. So the first thing that I need to do is I need to check whether the solution exists or not. That you can check from here very easily. Okay, x squared plus y squared has to be less than L1 plus L2. Now if that is satisfied, that means the solution exists. Then what we do is we find the negative solution first. Okay, because using the law of cosines, we use this. So we get the top solution first. Okay, so from here we find the top solution, which is minus of theta 2. And once you get minus of theta 2, what you have to do is you have to find what is corresponding theta 1 that we can find from that tan relationship. Okay, now once I get that, I can find the other solution. How do I find the other solution? Because if one solution is minus theta 2, the other solution is going to be plus theta 2. Okay, so that is what is what was shown here, that we have two solutions, and that is plus and minus. Now this is the simulation. Okay, so in this simulation we are given so here L1 is equal to L2 is equal to 5 units. Okay, and I wanted to go to some position. Okay, let me say I wanted to go to 4, 4, just for example. Okay, I want the end effector to go to that point in space. So it is computing theta 1 and theta 2, okay, which will take it to that position. Okay, now there are two solutions. This is one solution and there is another one solution, theta 2 and sorry, it is the other solution is theta 1 and theta 1 dash. So for one solution, this is one graph. For the other one, this is another one, because there are two of them now. Okay, so the first one is taking this solution, this graph is taking this solution, and the other graph is taking that solution. Now how are we simulating it? Exactly the same way in which I did the forward kinematics program. Okay, so I know that theta 1 is going to move from 0 degrees to some amount, theta 2 is going to move from 0 degrees to some other amount. I divide each of this by 100 units, and then in a for loop I keep incrementing them. Okay, and then I find the joint positions, joint 1, joint 2. Okay, and by using joint 1, joint 2 and joint 3, I can plot these points, joint 1, joint 2, joint 3, and as it is moving, I simply join those points by straight lines, and that makes a simulation. Okay, so the procedure is exactly the same. You define your axis, make your DH parameter table, find the transformation matrices, multiply each of the matrices, get joint 1, joint 2, joint 3. Okay, now once you get this 1, 2 and 3, You are getting those points. Now, what are those points? They are the last column of your transformation matrix. They are the corresponding x and y. So all you have to do is to just plot them. Okay. So in inverse kinematics, the first thing that we do is to get the solutions. Then what we do is we simulate it, just the way we did the forward kinematics. Okay. So this has actually two parts. Now let's look at the simulation again. The first solution is the positive solution. The second solution is the negative solution. So this is one solution. The other solution is that one. Okay. So let's see it again. So for the same position, we are getting two solutions now. This is one solution. The other one is, this is the other solution. Okay. So now let's look at the program, of how the program is written. It is very similar to the way the forward kinematics was written. A part of this is the forward kinematics in a way. Okay. So let's look at the program. So I go back to MATLAB again. Now in MATLAB, this is the inverse kinematics program. Okay. So the first thing that we need to do is we need to define the link lengths L1 and L2. This time it is 5 and 5. In the previous program it was 10 and 10. These are link lengths. It can be anything. Okay. Now the input to inverse kinematics is the position x and y coordinates that is desired, and it has to find what is the corresponding angle, right? So here the desired position is 4 and 4, which is given here. I can change it and get different solutions. Now we also have to specify the initial position. So we are specifying initial theta 1, theta 2 equal to 0. Okay. Now the first solution using Craig's geometrical solution is theta cos 2 is equal to x squared plus y squared minus L1 squared minus L2 squared divided by twice L1 L2. From here I'm getting what is cos 2, taking the negative value of theta 2 for the first solution. Okay. So this is the hands elbow up position which we are doing first. Now from here you can find what is beta and you can find what is phi. Okay. So once you find beta and phi, we can say beta minus phi will give you theta 1. Okay. Similarly, the other solution is going to become plus cos, and it is going to become phi plus beta. Okay. So we are finding both the solutions by using that geometrical method that I just explained. Now once you find the first solution, you have to find the second solution. So this is the first solution, okay, where we are taking negative value of theta 2 and then finding. The second case, we are taking the other solution as taken the positive value of theta 2. Okay. So what we are doing here is we are finding both the solutions. Now once you have found both the solutions, then what you have to do is you have to plot. Finding both the solutions means you have got theta 1 and you have got theta 2 now. Now you have to plot two sets of solutions. So now you have to plot. Plotting is exactly the same in which we did the forward kinematics. So you have the DH parameter table, and then you have a transformation matrix T1, T2, and T3. So for the first joint, we multiply T1 into T2, okay, and to take the last column, we multiplied by 0, 0, 1, getting the first position in homogeneous coordinates. So for getting the second position, we multiplied by T1, T2, T3 into 0, 0, 1, again just to get that last column, the first two elements of the last column. That is going to give me my x and y. And here, what we have done is x and y again, like in the previous case. So this is an array. It consists of the x coordinates of the 0th joint, first joint, and second joint. Similarly, the y coordinate of the 0th joint, first joint, and second joint. Okay, then we plot it exactly the same way. X and y are plotted, and they are connected by blue lines. And as it is moving, it is going to keep plotting. Okay, so there is you can see here exactly the same thing was done. So the initial theta versus minus final theta divided by 100, divided into 100 divisions. So theta 2 is equal to the theta 2 final minus theta 2 initial divided by 100 divisions. Okay, and then we run a for loop which is shown here. For I is equal to 1 to 100. So it will start incrementing from I is equal to 1, then 2, 3, 4, like that up to 100. Okay, so it will start from 0, 0 and it will end whatever was the value that was found in the inverse kinematics program. Okay. So this is the way inverse kinematics is done. And let us run it and see. So let us see what was given as the link length. The link length was 5, 5, and the final position of the end effector is 4 and 4. Okay, so in inverse kinematics, the input is 4 and 4. We want the corresponding joint angles. Once we get the corresponding joint angles, we have to simulate it. That means dividing the joint angles, the total motion of the joints, into 100 divisions, and then doing forward kinematics for each of those. So let's run it and see what it does. This program is a little bit more involved, so it will probably take a little bit more time. I'm running it online, not on the system, so it is taking a little bit of time. So there are two graphs that will be made. Okay, so this is one graph, and there is another one which will come up. So the left side was one solution, the right side is another solution for the same 4, 4. When you run this on a bigger laptop, okay, I'm running it on a tablet, so it is taking a lot of more time, and the screen is very small. But when you run it on a PC, then you can actually see both the graphs together. Okay. So this corresponds to the position of end effector x and y as 4 and 4. Okay, so what we'll do is let us run it again and see for the end effector position 4 and 4, what is the various angles of theta 1, theta 2, two sets of angles. Now, if you have a larger manipulator like 6 degrees of freedom Puma, okay, then you can have larger number of solution sets. Okay, so as you are going towards the singularity, your number of solutions will start coming down. But if you're somewhere in the workspace for the Puma, you can get up to 6 solutions. Okay, now this is showing us, so you can see that the end effector has reached the position 4, 4 coordinates. Right? Now let's change the coordinate and see what it does. Let's say we do it 6, 6. Okay, let me just change this coordinate and make it 6 and 6. So this is my 6, and let's say 6, or make it so let's make it a little bit straighter. So let's 5 and 5 is 10, so we can make it 9 and 9. Okay, 9 and or a little bit higher, let's take it. So let me make the x coordinate 2 and that one 8, just for fun. 2 and this one is 8. 2 and 8. Okay, so now let me see what it does. Let me shut this down. Now let me run it and see what it does. So x is 2 and y is 8. So it has started plotting the first one. So the first thing it does, it checks whether it is inside or not. Okay, so now it has plotted the first one. You can see where the end effector has gone. It has gone at x is equal to 2 units and y is equal to 8 units. Okay, similarly, the second solution also, it has taken it at 2 units and 8 units. Okay, so yeah, so if I click there, you see it says 2 and 8. Okay, now this is the way we do inverse kinematics. This is the way you can write a program. There are of course many ways of writing a program, and this is a simple way of writing a program. Even for complex manipulators, you can do it like this. Okay, so this is just to give you an example of how a MATLAB program is written and what is the procedure for writing a program to get a solution and also to do simulation of manipulator systems. Now you can write it very easily in MATLAB, and the advantage of MATLAB, as I said before, is that matrix multiplications are very easy in MATLAB. So it's very, very easy to do these computations and then to plot. It has very beautiful plotting functions. So this is the way forward kinematics and inverse kinematics is done. And so today we looked at forward kinematics, inverse kinematics, how to write a very simple MATLAB code. I'm sure you can write it yourself, but you should write it yourself and try. Okay, once you write it yourself, errors will come, but then you'll have other ways of writing. Okay, and maybe you can think of different ways of writing, faster way of writing this code. So today we'll end here, and then we'll proceed on to the other topics. And as we go along, as I keep doing the theory classes, I'll also be talking about MATLAB programs and MATLAB codes, where each of whatever we do, forward kinematics, inverse kinematics, dynamics, control systems, we can all write MATLAB codes and then do them using MATLAB. So we'll stop here today. Thank you.